Greetings, Earthlings. Today we're going to go over where pi comes from and why the circumference of a circle 2 pi r and the area pi r squared. Now we're not going to go over these in great detail, but I think just enough that it will satisfy your curiosity for now. And I'll also put a lot of links in the description, so feel free, and I encourage you guys to explore it after this video. Alright, so let's start with pi. So this has to do with the Greek letter, which actually has the P sound as well and stands for perimeter. But let's back up. So we have a circle. Obviously, many of you probably know pi has to do with circles. So let's see what this is. Now, here's the thing. Let's say we want to find the circumference. Where would we even start? Like, how do we measure this? So let's go back to basics. So let's say we have a string. So you could take a shoelace or any piece of rope you guys have. You could take maybe a little USB cord or something from like a mouse or whatever, and just try to we want a rope or something because it'll be flexible. So and wrap it around. So let's say this is a radius of 1, and I'm going to actually draw a hexagon made up of little triangles. Alright, so these are all 6 equilateral triangles. And why are we doing this? So this is a radius of 1, and if you measure this out, you'll see there's 1, 2, 3, 4, 5, 6 round segments. And clearly in the diagram you can see that each round segment is a bit longer than each straight segment. So if the radius is 1, or in general if it's r, we would need the circumference would be more than 6r, just according to this diagram, because we need 6 round segments, and 6 round segments are more than 6 straight segments. Now, we're already well on our way to figuring out where pi comes from. So that's very much how people might have done it back in the day. You might say, well, you know what, it's 6 and change. Maybe it's about 6 1/3. So like 1, 2, 3, like you're kind of doing, you have a little bit left over, and you eyeball it, and you say that's about 1/3 of a radius. Not a bad approximation. So let's go over how Archimedes, and not just Archimedes, a lot of ancient cultures did this independently. And one of the themes in this video is going to be how pi, it has been discovered and rediscovered by many, many cultures. And in fact, one of the reasons that I love mathematics is that it's about good ideas. So it's inherently not about discriminating or any silly things, because mathematics doesn't care where you're from or what your background is. They just care, are your ideas good? And many cultures have made great contributions. So that's one of the reasons I love mathematics and pi in particular. All right, so in order to attack this, we are going to, that's right, use our hammer again. So what's easier than a circle? Polygons. In fact, in the previous video, we went into polygons. And what was our hammer for polygons? So one of our hammers was triangles. So to attack the circle, let's see what we can do with polygons. So in fact, Archimedes, and I'll put a lot of links in the description, this was the approach that he and his followers and other cultures have used historically to get a nice value for pi. So pi is approximately 3.141 blah 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 blah, whatever, 15, I don't know, I'm not a pi wizard. Where do these digits come from? So like I said, just by eyeballing, we might get that this is 6r. So if you double this number, you'll get 6.28 blah blah blah, and in fact that's our number of 6 something here. So that's this 2 pi r. So if you plug in 3.14 times 2, you'll get 6 point something times r. So what did Archimedes do? He said, let's approximate this with a polygon, let's say a hexagon. Well, we know that in fact the true circumference is a little larger than just the perimeter of this hexagon. And he said, no worries, we know that it's a little larger than this, but what if we take a hexagon that's outside of the circle, or rather, see, this hexagon is called inscribed because it touches it on the inside. We're going to circumscribe a hexagon. So this hexagon would touch at these midpoints, if I've drawn it well. What's the point of drawing both of those hexagons? So if we draw, in other words, one of them is slightly larger, and we know the true perimeter or circumference of the circle is going to be a bit larger than the smaller hexagon and a bit smaller than the outside one. Let's convince ourselves a little bit, because that's actually number 2. So I have 2 rarely answered questions. I'll get to number 1 in a minute. So number 2 is going to be, why is this larger one actually has a larger perimeter than the circle? That's not necessarily obvious, because perhaps the SQUIRCLE, trademark. So perhaps the circle zigzags, and for example, here's an example where you have something that has a larger area but a smaller perimeter. So here's a square, but I could have something that goes like this inside. So theoretically, this could have a larger perimeter than the square rectangle. So because of that argument, and by the way, if you want more on this idea, you can go see my video on fractals. I think you'll find that pretty interesting. All right, but let's just focus on, let's say, this segment right here. So I'm going to blow it up. So it's going to look like this, and then we have this rounded bit. I'm going to just give you guys like an intuitive argument, not a very rigorous mathematical one. Why would these 2 combined segments be longer than this one? Well, if this is a straight line, we'll see in a future video when we go over the triangle inequality that would be the case. But this is curved, so maybe the curved one is longer. Well, the way I think about it is, imagine we take this curved thing and we press on it and we push into this corner, right? Then we would, like, imagine this is a rubber band and we're going to press till it hits that. Then they would have exactly the same length. But since we needed to press into it, that means we just made it longer, right? So therefore, the original one is shorter. I like that argument. So, using that argument, now I feel fairly safe in saying that the circle that we're interested in is indeed has a smaller perimeter than the large hexagon and a larger perimeter or circumference. Circumference, perimeter, interchangeable. That's just for circles. Than the small hexagon. All right. Now you might say, well, how is the hexagon going to give us pi? You're right, it's not. However, what we are going to want to do, and this is where I said I'm not going to go into the nitty-gritty. Archimedes had some nice derivations, but the idea is if we take larger and larger polygons, so let's draw a different diagram. So here's our circle again. And we could think of it, whether you're doing an inscribed on the inside or circumscribed, doesn't matter. I'm just going to kind of make this many sided, right? So ignore my terrible diagram. The point is, if you create a polygon out of many points, you'll notice that it starts to approximate the circle. These little gaps, these discrepancies, are almost insignificant. So the key idea is, we started off, let's say, with that hexagon on the inside and the outside. So we know that the true circumference is in between those values, and because those are nice polygons, we know how to calculate them, we know how to find things. So we're going to make our polygons larger and larger. Now, I don't mean size-wise, larger, many and many more sides. So we're going to keep doubling the number of sides. And as we increase the sides, so let's say this is on the inside, the outside is a terrible diagram. The point is, these little errors between the inside and the outside are going to shrink. So, in fact, if you think of a circle, you can think of a circle as an infinitely sided polygon. If I have you could try this experiment. if you have computer software, you can find images. If you look at, let's say, a 1,000-sided polygon, you won't be able to tell whether it's a circle or a polygon. So, bottom line is, as we create polygons, which are fairly basic mathematical things, we can get a tighter and tighter bound. Like, we can now basically zoom in on what pi is. So, doing that, we will find that indeed, for let's say like when n is 1,000 sides, the value of the circumference is between two very tight values. It can be between like 3.13 and 3.15. It's going to be even tighter than that, but just as an example. So let's just say we found, it wouldn't be the circumference, so rather we are going to find the circumference is in between a very tight range. So let's just say it's 6.27 to 6.29 or 6.279999 to 6 point whatever. Now, from there, we are going to conclude, and if you guys are already starting to have a question, I've had the same question and we're about to get to your question. So, how do we know? Let's just assume that the circumference formula is 2 times some mysterious number times r. Because we found a really tight range, let's say this is approximately 6.28 times the radius, and we know there's 2 of these. You divide this by 2, there's an r here, so you find this mystery number, which we'll call pi because it's related to the perimeter, must be 3.14. So in other words, the historical approach is to approximate pi gradually by taking larger and larger polygons. Alright, if you're confused, where did I just get this? That is actually a really good question, and that's why I put it here as one of the rarely answered questions. That people just kind of assume, well, that's the formula, let's just find what pi is with the polygons. So, what I want to go over now is to figure out where does this 2 pi r come from. So that's going to be question number 1. So there are many ways to think about this, but let's try it this way. The first way you might think about is kind of just experimentally. You have a circle, let's say it has a radius of 1. And you've measured it. You took you had a rough measuring rope, and you figured out that the circumference is about 6.28. Let's just say approximately. Now you drew a larger circle. This one had a radius of 2, and you figured out for this larger circle, the circumference also doubled. So if we double the radius, you found. You didn't theorize, you actually measured and found that it's going to be about 12.56. So after doing this a few times, you get the idea that, oh, if I scale my radius, the perimeter scales with it. In other words, it's proportional. This little symbol that I've drawn on the right here, this symbol, is the math way of writing proportional to. In other words, if I'm proportional to you, let's say like I am half as strong as you are. So that means if I get 5 times stronger, then you will get 5 times stronger. In other words, we stay in a ratio of 1 to 2. So if I multiply me by 5, you have to multiply you by 5. So that's what I mean by proportional. There's the same multiplier. So by measuring this, we've noticed that the perimeter scales with the size of the radius. So that tells us, or suggests, that the circumference is proportional to the radius. So you might ask yourself, what might be the alternative? Well, the alternative might be you can be proportional to the radius squared. Maybe you're the radius squared plus 3 times the radius. Or not, the numbers don't matter, but it might not just be the radius. It might be 1 divided by the radius. So just empirically, through measurement, we can get pretty confident that this is in fact proportional. In other words, it's some constant that we have to find. That's going to be our 2 pi bit. And through measurement, we figured out, yes, it indeed is linear. If I triple my radius, my perimeter or circumference triples. That's a hand-wavy first argument. From there, let's make it a little more rigorous. So let's use our hammer again and think of a circle as a many-sided polygon. And let's just focus on one of these segments, such as this segment right here. Now, clearly for polygons, if I double each of these little segments, the perimeter will double. Everything's doubled. But like we said, for the curved circles around, it might not be as obvious, but it might help you to think either to focus on this little segment and realize, hey, if this thing doubles, then that curved bit will also scale up and double. Or you could just think, if we think about like a 1,000-sided polygon, remember what we said, like the more sides you have, it's almost like a circle. And in fact, infinitely sided is a circle. So for like let's just conceptually think of 1,000 sides. So if we double our 1,000-sided polygon, the perimeter of the circle will also double because it's very close to that polygon. We're approximating it very well with many sides. So with that consideration of approximating it with our polygon, that being the hammer because polygons are simpler than circles, we can be pretty confident that the formula should be 2 pi r, or in more generally, it should be kr, some number times the radius. For convenience, twice the radius is also known as the diameter. We didn't have to do 2 pi r, we could have done 6.28 r, but you know, historically we just call it pi r because it's pi times the diameter. So now, and in fact, rather than hexagons, you could have drawn triangles to start with. So anyway, hopefully this is making sense to you guys. So that's why this formula has the shape that it does. And the thing we did before this in the beginning of the video was to figure out how do you actually find that exact number. But like I said, most times they'll just assume this is the form, and I was asking myself, well, how do we know that's even the form of the equation? All right, so hopefully that answered that question. If not, please shoot me a comment. All right, so now that we figured out, and if you do this, that's just the first way of getting pi. First, I mean historically. As people develop more mathematics, they found brilliant ways and many, many other ways of getting pi. So for example, when you guys study calculus, which I encourage you to do, it's really interesting, you will find many other ways of representing pi. Here's just one cool one. Pi divided by 4 is this infinite series. It's 1 minus a third plus a fifth minus a seventh plus a ninth minus an 11th and onwards to infinity. If you think this is the only way of doing it, there are actually many, many more. Like for example, the Indian mathematician Ramanujan had some really amazing stuff on it. So I encourage you to check it out. I'm going to put some links in the description. Alright, so now we're going to go to the kind of second half of the video. This will be a little shorter, but this is pretty much the heart of the video, and this is using our hammer in a more traditional way. So now that we assume we agree and take for granted that the circumference is 2 pi r, now we can figure out where does this area is equal to pi r squared formula come from. Alright, so let's take our circle. The perimeter of the circumference is 2 pi r. So just to remind you guys, what that means is if we took a string and measured it all around, and this is the radius, it would be 2 pi r. Now, I want to find the area of this. So, hammer time. So, what's simpler than a circle? Polygons, triangles, stuff like that. Straight, things with straight sides. So we're going to chop this up into, not pizza slices, but little triangles and things like, well, for now we'll start with pizza slices, but then you guys will see. So let's say we're going to chop this up. Now, yes, these are pizza slices and they're round. This is not straight, but we could pretend that they are straight. Now, what do I mean pretend? As we said before, this is the beauty of this whole thing. For maybe a hexagon, that's not a really good approximation. But remember, this, imagine like a 1,000 sided polygon. If this is 1,000 sided, then the straight part versus the round part will be almost the same thing. So our error will go down and down as we take larger, more sided polygons with more sides. So here's the next part. So all of these are basically little triangles, and now we're going to peel it open, like an orange or a snail or whatever you want to think of it as. So we're going to peel it open, and it's going to look like this. So there'll be, a lot of these triangles. And remember, there are a lot, think of it as like almost infinitely many really tiny triangles. This whole thing is 2 pi r. Remember, this is the circumference of the circle that we just peeled open. When we peeled it open, each of these heights, that's your radius. So let me just draw this diagram here. That's going to be the height. So each of these lines is each of these lines. These are all r's. So what is the formula for a triangle? It's 1/2 base times height. So our base we'll get to in a second, but our heights are all the radius, right? So let's say we have a base here, we have a base here, we have a base here. So think of this as area plus area plus area plus area. We're adding up a lot of areas. So we can even call this base the entire circumference divided by the number of these triangles. And let's see what happens. So let's call this individual base will be 2 pi r over n, where there are n triangles. Well, when we added the areas later, you're going to have 2 pi r over n times the height times 1/2. That's your area formula for a triangle. So it's 1/2 base times height. So again, it's 1/2 2 pi r over n times r. But then we're going to do this n times because there are n triangles. So when you add up all of those over n's, n times, the over n's will cancel. See if you got that. So essentially what we're doing is you can think of all these triangles as almost just like one fat triangle that's kind of just like one thing with a base of 2 pi r and a height of r. So what is 2 pi r times r? That's 2 pi r squared, and what's 1/2 of that? That's pi r squared. So let me just write that here. So it's going to be 1/2 2 pi r times r, and there is, if you simplify that, there's your area formula. So all we did is use the area of a triangle and the circumference and peeled open our circle. All right, I'll leave it there. I know that might have been a little not the best explanation at times, but I hope that helped a lot of you guys. I want to just throw out a fun fact. This is something that, I've taken calculus and something I didn't realize at the time. So for those of you that either want to take calculus or already taken calculus or just heard of calculus, when you take it, here's a really fun fact. The area formula is pi r squared, and in calculus, one of the things you're allowed to do is, I'm not going to get into it, but basically, I'll give you a taste, and if you're curious, go and study more. If you take this 2 from the pi r squared and drop it down, you're going to get that 2 here. And then if you make this exponent 1 less, the r squared will become r to the first. So in other words, let me give a quick thing in calculus. So let's say you start off with a formula like 3x squared. And then in calculus, we learned this rule where this is called the derivative. Don't worry about it, but the idea is if you drop this number down, you multiply it by what's there, so it'll be 2 times 3, and you make the exponent 1 less. So it'll be, the 2 goes to a 1. So when you learn calculus, you'll find yet another way of relating the area and the circumference, and it's not a coincidence that they have these numbers. This 2 has to do with that 2, and that 1 used to be a 2, which just dropped down in the power because we're going down from area to circumference. If that made no sense, don't even worry about it. I'm just trying to make you guys a little curious about it. All right. So hopefully that gives you guys some ideas, answered some questions. If something was confusing or if you wanted to see more, you have any thoughts whatsoever, let me know in the comments. I'll see you guys in the next video.